Welcome everyone. I'm going to talk about AnySeq GPU, a novel approach for faster sequence alignment on GPUs. My name is André Müller. I work in the high performance group of Professor Bertil Schmidt at the Johannes Gutenberg University Mainz, Germany. This is joint work with Richard Membarth, Roland Leißa, Sebastian, which work on the AnyDSL compiler framework. So as the title suggests, we are dealing with biosequence data like DNA or RNA, which are essentially strings of letters called base pairs in this context. And these sequences fall into three broad categories in practice. Short reads, which are the most prevalent ones, which are 100 to a few hundred base pairs long. Long reads, which can have 1,000 to up to 100,000 base pairs. And genomes, which are in the range of 1 million to several billion base pairs. Typical dataset sizes are a few gigabytes, like a typical short read dataset has 50 gigabytes or so. And this amount of sequencing data has been rapidly increasing in the last few years. And the NIH, for example, estimates that around 40 gigabytes of sequencing data will be produced worldwide by 2025. So this is why we need fast processing algorithms. One of the most important and frequent tasks in bioinformatics data processing pipelines is sequence alignment, which is needed for assembling whole genomes from short reads or for correcting sequencing errors made by the sequencing machines or detecting mutations or to match individual short reads to a site in a genome. The input for a sequence alignment is a pair of strings, e.g. DNA, with the letters A, C, T, G. And the output is either an alignment score, which is a measure of the minimum edit distance to make these two sequences identical, or an alignment score plus an optimum alignment, which is the actual positions of deletions, inserts, or substitutions to make these two sequences match optimally. Optimum alignments are computed using dynamic programming, for example, with the Smith-Waterman or Needleman-Wunsch algorithm. And in this short example of a local alignment, we have our two input sequences called the subject sequence and the query sequence, and the following recurrence relation. If we go down diagonally, we add a substitution score of +2 if the two characters match, and subtract -1 if they don't match. If we go straight down, we introduce a gap in the subject sequence and subtract a gap penalty of -1. If you go to the right, we add a gap in the query sequence and also subtract a gap penalty of -1. So for each cell that we want to compute, we have to know the upper, the left, and the upper left value. And after the matrix is fully computed, we determine the optimum alignment path by tracing back the values of the optimum alignment. We usually distinguish three types of alignments: global alignments, semi-global alignments, where gaps at the beginning or the end of a sequence don't contribute to the alignment score, or local alignments, where we can essentially restart the alignment anywhere in the DP matrix. And also two common types of gap penalties are the linear one, as in the example earlier, where we subtract a constant for each new gap, and a so-called affine gap penalty, where opening a gap is usually more expensive than continuing a gap. And also this affine gap penalty requires the introduction of two additional dynamic programming matrices, as you can see in the recurrence relations to the right. And finally, the substitution function sigma can be more complicated than +2 for a match and -1 for a mismatch. For example, substituting an A for a C might be more expensive than substituting an A for a T. Performance is usually measured in gigacell updates per second, GCUPS for short. And to give you a few rough ballpark numbers, current state-of-the-art CPU libraries using AVX 512, for example, can achieve up to 220 gigacups on a 32-thread machine. while current GPU algorithms are around 40 to 260 gigacups for the same task on an NVIDIA GV100. So seeing these numbers, one could think that there is no clear advantage in using a GPU over a CPU. Our new approach changes this situation in favor of GPUs, mainly by minimizing memory accesses in relation to computations. Main tool for that are warp shuffles for fast inter-thread communication. We also use floats instead of integers for score computation, and employ half-precision arithmetic if the hardware supports it, for effectively doubling the amount of computations that can be done per thread. So if you've never programmed on a GPU before, think of a SIMD machine with 32 lanes where 32 threads in a so-called warp are executed in lockstep, which means that we want to avoid branch divergence. And so the first step in our algorithm is to transform one of the input sequences, in this case the subject sequence, into a so-called scoring profile, a lookup table for the substitution scores. We do that by applying the substitution function sigma to each letter of the subject sequence and a potential letter of the query sequence. So we have this 4-dimensional array in this case, where if we have a G in the subject sequence, we get a +2 if the query sequence has also a G, and a -1 if the query sequence has a -1, has a C. And this profile is stored in shared memory. So we have the following situation. We have our subject sequence, which is now indirectly accessed using the scoring profile in shared memory. We have our query sequence. We have initial values for the columns and rows, which depend on the alignment type. And we want to compute our dynamic programming matrix. And as we've seen before, we need the values above, to the left, and the upper left for that. This is usually done with a so-called wavefront approach, and the current GPU libraries and also our old AnySeq 1 library computes one column of the DP matrix per thread, which means that the threads also have to be offset by one row, because the left and upper left values for thread 1 have to be first computed by thread 0. First step to increase occupancy is to let each thread compute k columns instead of just one. So if we have, in this example, k equals 4, we can compute 128 columns per warp of 32 threads. So for each thread, we need at least k registers for storing row values. Note that we only need k instead of 2 times k, because the values from the previous row can just be overwritten with the values from the current row. But we also need the value to the left of the current strip that's computed by a thread, and the diagonal value. We also need the query character, which we'll see will be different for each thread. Computation proceeds then in a wavefront, as we've seen before, where more and more threads become active because the values to their left have been computed. Now let's look in more detail what happens between iterations. So suppose we are in iteration number 3. The blue cell values have already been computed. We want to compute the values in the red cells, and we've already loaded the correct query characters for each thread. Each thread can now compute its k values by looking up the substitution score using the scoring profile, and it knows the values to the left and the diagonal values and the old values from above. When we now start the next iteration, we do the following. First, we overwrite the new diagonal value with the old left value. Then we use warp shuffles to communicate the rightmost value of a thread to the leftmost value of the next thread. Also, the leftmost thread has to set its left value to the initial value. Now that all values the current computation depends on have been set up, we now need to make sure that each thread has the correct query character. So the query character that thread 1 needs in the current iteration is the one that thread 0 needed in the previous iteration. So we use a warp shuffle up to communicate the query characters from threads with a lower ID to threads with a higher ID. And only the first thread has to load a new query character. Since loading from global memory is expensive, we try to avoid that by only loading new query characters every warp size, so every thread count iterations. For that, we have an additional register in each thread that stores a query character. And in all iterations between these global loads, we can use these additional registers to shuffle down query characters so that the leftmost thread can obtain a new query character, which itself, of course, shuffles up its old query character to the next thread. If a sequence is longer than k times warp size, we have to divide the computation into several passes. So in this example, we have a k of 4 and a warp size of only 3 threads. Then we divide the computation into 12 columns per pass. We of course have to make sure that the rightmost values of the previous pass are accessible to the next pass, since it needs them as their leftmost and diagonal values. As we've seen, the rightmost value in each thread is communicated via shuffle up to the next thread. So in a similar way, we can then use the rightmost value in a warp and shuffle these values down into additional registers, store these in a temporary storage, and then retrieve them and also shuffle them down, just like the query characters, to supply the next pass with the correct input values from the left. More recent GPUs also support half-precision arithmetic, like for example NVIDIA's Ampere architecture, which lets you apply the same operation to the lower and the upper half of a 32-bit field. We used the addition and max instructions for score computation and these two conversion intrinsics to convert between floats, so 32-bit floats and 16-bit half values. This allows us to compute two independent alignments in parallel in the upper half and the lower half of a register, meaning that we now have 2 times k cells that can be computed per thread. One alignment, for example here between sequence A and Q in the upper half, and a second alignment in the lower half here between sequence B and Q. One potential drawback of using 16-bit floating point values is, of course, the limited range, which could lead to overflow when we have very long sequences, and also the substitution scores. So the values in the substitution function are fairly large, which is normally not the case. They're usually small, so less than 10. One possible solution is to detect such overflows and just rerun the alignment with the 32-bit kernel. We implemented our algorithm using the AnyDSL compiler framework, which allows you to create high-performance domain-specific languages as libraries in a language called Impala. So unlike traditional approaches where you have your own DSL compiler, or you have a meta compiler which translates a meta program into a program which is then translated to machine code. you only write everything in one language. AnyDSL's main feature is guaranteed partial evaluation. So unlike with other languages or compilers where you have to rely on compiler heuristics and have to essentially pray that certain functions will be inlined or certain constants will be propagated at compile time, a guaranteed partial evaluation means that you can rely on abstractions to be optimized away at compile time. So you can have data accessor objects that go through 10 different levels of indirection, and you know they will be optimized away at compile time. So this allows you to encapsulate algorithmic strategies in composable functions, and without the fear that 20 levels of composition will incur some kind of abstraction overhead, some abstraction penalty. And it allows precise control over which parameters shall be partially evaluated. So what should be optimized at compile time. Another advantage of AnyDSL is that it comes with integrated mapping files for different architectures. So for example, NVIDIA GPUs or AMD GPUs, or it also has constructs to map computation to FPGAs or to SIMD vectorize certain loops. So what does this look like? Here we have a short impala function which maps an integer to its square. And those of you who are familiar with Rust will probably recognize the syntactic similarity. In this next example, the function foo has this @ sign in front of it, which tells the partial evaluator to generate specializations with respect to parameter values, which means that if x is known to be 1 at compile time, the partial evaluator will generate a specialization of foo with x held constant to 1. We can also have more fine-grained control over partial evaluation. So in this example, bar will be specialized if k is known at compile time. Also note that bar is a higher order function. So the third parameter, mapping, is itself a function that takes two floats that are mapped to a float. And also those higher order parameters will always specialize, meaning that if you supply a concrete function for the parameter mapping at compile time, bar will be specialized with respect to this parameter. Another nice feature of AnyDSL is that it allows you to write your own iteration functions using the for protocol. In this case, range is a function that takes the iteration bounds and it gets a third implicit parameter, which is a higher order function, which is essentially the body of the for loop. So the body of the for loop is called with the different values for I. The predefined function unroll lets you write for loops that are guaranteed to be unrolled. So it's like pragma unroll, but with the guarantee that it's partially evaluated and unrolled. Thread parallelism is expressed in a similar way. You have this function parallel, which is also predefined in Pala's runtime, where p is the number of threads, and then the iterations from 1 through 7 are then distributed over the p threads. GPUs are programmed in a similar manner. In this case, you call the function accelerator with a device ID, get back an object called ACC here, which provides a function called AnySeq, which you can use to start a kernel with grid and block dimensions of your choosing. And in the body of the for loop, you can then write your kernel with access to block index and thread index. To evaluate our implementation, we used 4 different systems: a dual Intel Xeon Gold system with 2 NVIDIA GV100s, a dual Intel Xeon with NVIDIA RTX 3090, a DGX A100, and a dual Xeon Gold with an AMD MI100. The two CPU libraries we tested were the popular SecN library and our old implementation in AnySeq 1. GPU libraries tested were our old AnySeq 1, our new AnySeq GPU, NVBio, Gazelle 2, and Adapt. The NVIDIA systems we used CUDA 10.2, and the AMD system we used Hippify for compiling the CUDA code to run on the AMD card, and of course our NEDSL implementation runs directly on the AMD system. In our experiments, we used artificial reads created from human chromosome 10, first sets of Illumina reads with lengths from 125 to 4096, which were aligned pairwise, and second PacBio reads with lengths around 21 plus minus 6000, which were aligned to the original chromosome 10. So PCIe transfer times to the GPU are usually negligible. This is, for example, for a typical dataset, it takes 870 milliseconds for the alignment computation and only 0.4 milliseconds for the PCIe transfer. So transfer times are not included in the following. The following table shows performance in gigacell updates per second, short gigacups, for global linear alignments. Score-only computation, so without the traceback, and so this is the fastest scenario. There are three main columns for short 125 base pair reads, for 512 base pair reads, and for long PacBio reads. The two CPU libraries perform more or less the same, around 200 gigacups, while SecN is a little faster than the old AnySeq 1. The GPU libraries, we can clearly see that AnySeq GPU outperforms all other GPU libraries by up to an order of magnitude. Also, note that the performance of the other GPU libraries drops significantly when the reads get longer. And the picture stays more or less the same if you also compute the traceback, which is of course more costly, but the relative performance differences remain the same. In the following, we see performance comparisons for pairwise alignment of 125 base pair short reads. In the first row, we see the same scenario as before, global linear alignment, and to the left scores only, to the right with traceback. And below that, in the second row, we see global affine alignments. To the left scores only, to the right traceback. And we can also see that while affine alignment is slower, which is to be expected because we also have to keep two additional DP matrices, the relative performance differences between the libraries stay almost the same. Now in the upper right corner, we see the performance figures for semi-global alignments, also linear and affine with and without traceback. And we also see that AnySeq, which is the bluish bar, outperforms all the other libraries, also the CPU libraries. And the relative performance differences are roughly the same as in the global alignment case, which is also to be expected because the main difference between semi-global and global is the different initialization and a slightly different result retrieval. And in the bottom row, we can see the results for local alignments, which are slower still, because we also have to keep track of the current best alignment score within the DP matrix. So overall, global linear scores only alignment is the fastest scenario, and local affine with traceback is the slowest, which is to be expected. We see that AnySeq outperforms all other libraries in all scenarios. And also note that not all libraries support all types of alignment, which explains some missing bars. Next, we see the performance of AnySeq GPU for the pairwise alignment of short reads with different lengths. So from length 125 to 4096. To the left for a global alignment with linear penalties, in the middle for a global alignment with affine penalties, and to the right for a local alignment with affine penalties. We see that in all three scenarios, a read length of 512 is optimal for the NVIDIA cards, while at least for global alignments, the AMD card performs best for reads of length 1024. So we have seen that AnySeq GPU outperforms the other libraries, but how good are these results actually in absolute terms? To evaluate this, we did a theoretical peak performance analysis where we took the number of cores times the GPU boost clock divided by the cycles per DP matrix cell update, which should give us a theoretical peak performance. So for a global alignment with affine gap penalties, we need 7 instructions in our implementation, 4 maximums and 3 additions, subtractions, which can be seen in this row, cycles per cell update. Note that for the A100 and the MI100, where we use half precision arithmetic, we halve the number of cycles per cell update because we compute 2 alignments in parallel in the upper and lower half, as shown before. And given the boost clock that was reported and the number of floating point cores that each GPU has, we get a theoretical peak performance, and compare this to the actually achieved tera cell updates per second, so TCUPs, and get a efficiency of something between 82% and 95%. So on the V100, we are very close to peak performance, and on the other 3 cards, we get at least above 80% peak performance according to this analysis. To conclude, key takeaway points are: one can minimize expensive memory accesses by using warp shuffles for inter-thread communication. It's beneficial to compute many values per thread, as we have shown with our register tiling and half precision arithmetic approach. And we were able to achieve close to peak performance, outperforming all previous GPU and CPU libraries, and have for the first time a GPU alignment solution that's significantly faster than the fastest CPU library.